All right, we're back. We're on page 6 of notes 14 of Calc AB, and we're talking about approximating definite integrals. We just saw on the previous page that if we have a calculator, the number of rectangles we use is like, there's almost just no limit, actually. So what we want to do is just get good at the process. So that's basically what this page and the next page are about. So let's see if we can do it. So we're going to approximate this. The graph is given. I don't know if I'm supposed to draw. Maybe. Use two rectangles and a right-hand sum. Okay, so first thing I'm gonna do for two rectangles, do I have a picture every time? I guess I kind of do. Two rectangles, so from 0 to 3 to 3/2 is right there. If I'm gonna use a right-hand sum and two rectangles, I'm gonna draw it. So a right-hand sum. It's gonna go like here and then there. And then this one's like, is that a rectangle? I guess. I mean, it is. Like, that's what you do. So you're going to do, the base is 3/2, and then the first height is f of 3/2. I'm going to do everything in terms of f. So I don't really need that parenthesis, I guess. 3/2 f of 3/2 plus 3/2 f of 3. And then do we need to figure that out? Can I just use a calculator? Does anybody object to that? I don't think so. I won't even switch over. I'm just going to, so I'm redefining f of x to be 9 minus x squared. That's the number one mistake. Don't forget to redefine. And then I'm going to do 3/2 and then f of, I know f of 3 is 0, but I'm going to type it anyway. So I get 81/8, which let's do, uh-oh, where are you going? Okay, let's do decimals. So 10.125. 0.125. Now, I mean, that's like an awful estimate because we just ignored everything over here and also this. Like, that is a bad estimate. Function's decreasing. And our right, so since it's decreasing, the smallest it will ever be on each interval is at the right endpoint. So we're definitely getting an underestimate. So let's take a look at, so 2 with a left. So 2 with left. Okay, so then that's going to be like here. And then this has like the opposite problem where so much extra, right? And that's because it's decreasing. When it's decreasing, the biggest it will ever be is at the left endpoint, and we're assuming that we're kind of like pretending it's that all the way through. So if we do that, we're going to get like a crazy overestimate, right? If you're always using the biggest value, that's where giant overestimates come from. So this will be 3/2 and then f of 0 plus 3/2 f of 3/2. So let's see what the calculator says for that. You should be trying to type these in also. I mean, I think that's like the ideal scenario here. I got 23.625. So, I mean, I'm confident that it's somewhere between these. It's somewhere between 10.125 and 23.625. Maybe I should do a trapezoid, right? Just average those, and then that would be my trapezoidal sum, which I feel would clearly be better. If we had done a trapezoidal sum, we'd be cutting through here, and then cutting through here. Like it's an underestimate, but like not by a lot. So it's better than the left, and it's better than the right. The right's way under, the left is way over. Trapezoid is like under, but not by all that much. Not going to calculate it, but like keep that in mind. All right, 4. So to do 4, here we go. So 3 divided by 4 is 3/4, obviously. So should we do, I don't know, 3/4, 6/4, 9/4, and then 12/4. So if I'm doing a right-hand sum, I go like this, and then over, and this, and over, this, and over. And then it always just, it suffers from the fact that like that final right endpoint is at a height of 0. Like it just contributes nothing. But that's part of the method. I mean, it's not our fault. So each of them has a base of 3 divided by 4, right? Because it's 0 to 3, and we're doing 4 equals. So 3 divided by 4, then it's f of 3/4, f of 6/4, f of 9/4, and then f of 12/4 or 3. Okay, so let's see. I'm gonna punch that in on the calculator. Should I do a summation though? I'll actually switch. I feel like at 4, like I'm starting to not want to type these. So I might actually, I'm gonna do both just to show you that they do in fact give the same answer. F of 6/4 plus f of 9/4 plus f of 12/4, which is 3, decimal. We could have done the sum from I equals 1 to 4. 3/4 is the base of every one of them. And then the height is going to be 0 plus the base 3/4 times I. And then this, so 14.344. 14.344. Why does that sound weird to me? I don't expect you to know the answer to why something sounds weird to me, but I feel like that sounds a little weird. All right, left-hand sum, yay. Let's go back to the notes and try that. It's like, I don't hate this. I kind of like finding all these sums. You know, like it's something, I don't know, because it's not like super hard. It's kind of relaxing. Drawing them becomes a giant pain in the neck. 3/4, 6/4, 9/4. You might remember, if you learned to graph trig functions from me, you know that I do not like to simplify along the axes. It's just like, why? What's the point? And it's just easier to count if you don't. So what are you doing? Left sum? Okay, so left sum, we're gonna go straight across and then down. Straight across and then down. Hey, remember that time that I tried to do this with the real rectangles and it was a disaster? I hated that. It's the same day. I'm still making videos on that day. Oh, that's gross. All right, so this is gonna be, each has a base of 3/4, and then you're gonna do, you actually do f of 0, you do f of 3/4, f of 6/4, and then f of 9/4. So like, can we write a summation for this? Yes, we can. So what do we want to do? I'm gonna say it's still 1 to 4 because you have 4 rectangles. Each of them has a base of 3/4. Now the height, what am I doing? So I starts at 1, the first rectangle, but you don't want to add in the base, right? Because you want to do f of 0. So what I'm actually going to do is I'm going to say that it is 0 plus 3/4 times I minus 1. So why am I doing that? So to find the first, so the first one is like a little misleading, right? You're in rectangle number 1, 2, 3, and 4. So you're in rectangle number 1, but you don't want to add anything. You just want to do f of 0. Now for the next one, you're in rectangle 2, but you only want to add the base once to get to the left end point. So you can find the height of, let me do it again. You're at 0, you only want to add the base once so that you can find the height of the second rectangle. So that's 0 plus 1 times I when you're in the second rectangle. For the third rectangle, you want to add twice, so that's 0 plus 2 times I when you're in the third rectangle. For the fourth one, you want to do 0 plus 1, 2, 3 times I. So you're always doing I minus 1. When you're in the ith rectangle, you're in the fourth rectangle, you do I minus 1 times the base to get over to where you're going to find the height. So that's why I did this. To the calculator, I'm just going to punch it in, and you're going to take my word for it. So, because I can modify this thing like super easy, maybe. I get 21.094. 21.094. You can confirm that or check it. 21.094. Equal signs versus approximate signs. I'm gonna go out on a limb and say you're almost never, if there are decimals involved, you're almost never wrong using an approximately equal to sign, because very rarely are you getting the exact value. On the other hand, the College Board, and these videos are for AP Calculus, so like if you're watching them for another purpose, I don't know, figure out whoever's gonna grade your stuff and see what they want. For the College Board's purposes, 3 decimal places is like the exact answer. So if you're rounding correctly to 3 decimal places, you can just put an equal sign. I think that's so weird. The only thing, if it says approximate, so one place in here, you absolutely need an approximate. These are approximations. But after we've established that this is an approximation of that, now like all bets are kind of off. I think approximate signs are probably better, despite the fact that I'm not using them anywhere. I don't know. Do what I say, not what I do, perhaps in some instances. All right, I'm gonna stop here, come back and do the next page. So I will see you there.